Hi, hello and welcome to this short video. Today I present you what's new in dynamic general equilibrium modeling. Alfred Mausmer and I have published our third edition in March 2024. And dynamic general equilibrium modeling, that's still the place where macroeconomics takes place. That's the workhouse of macroeconomics. And there are a couple of issues and problems that I would like to point out today, in particular three problems, economic and methodological problems that we tackle in this new book by Springer, Dynamic General Equilibrium Modeling, and which might also be a source for your own research, an idea what you will pick up during your PhD studies. So let me get into some of the new material, some of the new 350 pages that we present in this book. All right, three things I would like to discuss with you. First is the curse of dimensionality, when we have many different ages, and even with modern technology, we run into problems how to compute it, because it may take days or even weeks to compute the solution of such a model. The second problem that I will consider today is the transition dynamics in a stochastic economy, where we still have methodological problems and where young researchers, young PhD students like you perhaps, will find a solution or find a field that's interesting, and you may come up with new results. I point out what we did so far and how you can improve it. And in the final part of this short talk, I would like to tackle an economic problem, which is equity premium. You know that stocks on average have a higher return than bonds, let's say 5 to 6% over the last couple, 50, 60, 70 years. And we have problems to explain this equity premium. Alfred Mausner and I will present some ideas, for example, disaster risk model, but these disaster risk models are hard to implement in large scale models, and here I think we have ample opportunity to extend the theory and tackle modern day problems. For example, in Germany right now, the government is taking on government debt to buy stocks and benefit from the equity premium in order to pay for its pensions in the pay-as-you-go system. And of course, this is very risky, very tricky, and you need to find models that endogenize the difference between returns in the stock market and in the bond markets, because if the German government becomes a big debtor, well, the equity premium might shrink. So this is a problem that you need to tackle with large scales, economic, dynamic general equilibrium models, and this is what we will turn to in the following. So let's consider first problem. You have a model with many heterogeneous agents. Perhaps you would like to study the distribution effects of economic policy, so a change in the income tax or something like this. And therefore you need to somehow consider that people are different. Some are rich, some are poor, some are female, some are male, some are young, some are old. And of course, they will be affected differently from a pension policy reform. And the present technology, computer technology, however, restricts us to only consider 2 or 3 dimensions of inequalities in our models. So what we do in our book here on dynamic general equilibrium modeling, we consider, for example, among others, a large-scale overlapping generation. So where people are different with respect to age. So they have age 20, 21, 22, up to 90. People are different with respect to their wealth. We have some poor people, some even without any wealth, 20, 30% without any wealth, and some rich people like Bill Gates. And people are also different with respect to their pension entitlements. So some of them have contributed to the public pension system and therefore accumulated large benefits or future entitlements of pensions, and others don't. Perhaps they were unemployed, or they were married and became parents or stuff like this. And of course, we need also to integrate a source of this heterogeneity, and we do it by looking at uncertain income. Some people are smart, others are less, and and some people become employed, others unemployed. So we provide uncertainty in income as a source of this heterogeneity. And then what we do, which will help you especially as a young researcher, as a graduate student, well, we compare our results for different computer languages. So here's table 11.3 from the book where we compare Julia, Gauss, and Python. And here we compare in table 73, we compare Fortran, Gauss, and MATLAB and consider which is the fastest computer language. For example, we find that Fortran is much faster than Gauss or MATLAB, and Python is faster than MATLAB, but slower than Julia, stuff like this. And of course, you would think, well, let's take the fastest computer language, let's say Fortran, but it comes at a cost. You need to learn the language. The computational time is faster, but it takes longer to program it. And for example, in the case of Fortran, you usually have to pay for the compiler, while programs like Python and Julia are free. So we discuss these kind of languages, and this will help you as a young researcher to find out which one you should pick. That's one new aspect in our third edition in comparison to our second edition. So we compare MATLAB, Fortran, Python, Julia, and Gauss so that you get an idea which one should I pick. Of course, it's an investment. If you, for example, start to learn programming with MATLAB, it might be hard to switch to Fortran or Gauss. And you have invested money, time, so you should know at the start and in the beginning of your research which kind of software you need. We discussed the curse of dimensionality problem and how you can reduce it so that you can compute it in 2 or 3 and perhaps 4 dimensions. And in this third edition, we also come up with a new solution method. For example, one is a Smolniak algorithm that we will present in this book. The second major problem that we consider in our book is one of the dynamics. So you probably know the business cycle model, real business cycle model that you study when we have a shock, let's say, to productivity or to government spending, and computes impulse response functions. So what are the dynamics after an unexpected increase of government consumption? Second form of transition that we also study in our book are transition dynamics. So typically we are interested in, let's say, the demographic transition. So as illustrated here in figure 1070 of our book, Dynamic General Equilibrium Modeling. And you can see that the old age dependency ratio increases from 27% to 44% over the next 100, 200 years in the United States, meaning that one worker has to take care of 0.28 retirees, and the OH dependency ratio is defined as the ratio of people older than 65 to people 20 to 65. So usually retirees to workers. Now, as a consequence of the shortage of labor, we observe that labor declines. It's hump-shaped, so it peaks when the baby boomers go into retirement, and as a consequence, capital per worker also looks hump-shaped. And this translates into behavior of factor prices as illustrated in the figure 1022 in our book. So wages go up and interest rates go down. So we expect that the interest rate goes down to 2% or even less during the demographic transition over the next 100 years. Some researchers even find that real interest rates will become negative. So our results are here in accordance with the hypothesis of secular decline. So expect lower returns from your savings, from your equity, from your stocks, from your old age savings. If you're a young person, probably it's going down. That's what's our expectation. Now, what does it mean for a public pension system? Now, for the United States, we expect that contribution rate goes up from 8% today to something like 13% in about 100 years. Now, this is not as dramatic as in continental Europe, where old age dependency ratios are much, much higher, or in Japan or in China. So, for example, in Germany, we expect that by the mid of the 30s, in about 10 to 15 years, contribution rates will be as high as 25, 23, 25%. And as a consequence, well, it's not really that attractive to go to work if you pay contributions, social security contributions of 25%, and you also have an income tax rate of 30, 40%. Well, you take back home about 40%, 30% of your gross wage income. Well, then it does not really make sense to get up in the morning and go to work. Okay, that's a problem that we faced, and we compute that the pension system can no longer be financed by a tax on labor income in 10 to 20 years in places like France, Italy, or Germany. So we have to rely on consumption taxes or similar to finance our pay-as-you-go pension system. Now the problem, well, this is quite easy to compute, and we illustrate this in our model. If we assume that the transition follows from a deterministic model. Now, we, however, struggle to include stochastic elements in our model. So what's happening if there's another great recession in the mid-20s, or if there's a debt crisis, or a war between China and Taiwan, or Russia and Central Europe? Now, all these kind of events might cause a disruption to our transition to the new steady state, and it's difficult to deal with it. And that's where young researchers like you might still find ample of opportunities to improve existing theory, both economic theory and our numerical methods. Now, we have new material in our book, Dynamic General Equilibrium Modeling. We provide 2 new chapters, 3 and 4, where we have second and third order local perturbation methods. And as we often cannot use local methods for these kind of economies which are in the transition, we also need more global methods which we can apply outside the steady state. And we have rewritten and amended chapter 5 on global methods, weighted residuals methods to a large extent. Now, there's also another problem with transition dynamics, and this is still an open question in research, so please feel free to add to this. Usually we do our perturbation around the deterministic steady state, for example, in the neoclassical growth model. That's what you learn in business cycles and macroeconomics 1 in your graduate programs. But this is not equal to the stochastic steady state, to the stationary steady state in a stochastic economy. So to understand this, if you assume that the technology shock is always, let's say, 0, there's no government demand shocks, and we are always in a deterministic states, people behave different than in an economy where you are afraid of shocks. So, for example, if we think, well, there might be a shock so that interest rates go down and that wages may go down, what we will do is we build up precautionary savings. And that's why, on average, in a stochastic economy, the capital stock savings might be higher than in a deterministic economy. And if you compute your solution around a deterministic steady state, you might not even consider the region that's the stationary steady state in your stochastic economy. And it also implies that you have lots of problems computing the transition. So let me illustrate this here on the whiteboard. So usually, let's say we want to compute a transition. Let's say today we have March 2024, and we want to compute the transition until 2100. And let's say capital stock behaves something like this. So it will first increase and then decline, something like this. That's our capital stock K. That's a very likely pattern for the next 50, 60 years, as you'll find out in the book. Now, the way to solve this is by backward shooting. So it's formally a 2-point boundary problem. So you know some variables, what they value in the initial steady state, and you know some of the the values of the variables in the final steady state. And the way you compute it is you start in the final steady state and assume that it's constant thereafter. And then you guess a value for the capital stock one period prior to the year 2100, which is the year 2099, and then you work backwards in time. And you then get a new value for your savings, for your factor prices, and from this you can compute a new guess for the transition parts. We argue at length in the book why you usually cannot start in the initial steady state, but you have to use backward shooting starting in the final year. But now assume you have a stochastic economy. So perhaps you do not know where you will end up in 2100. It may depend on the shock. You may end up any of these values here, depending on the shock. In economics, we learned about the phenomenon of hysteresis. So Blanchard and Summers, for example, they pointed out that one source of the European unemployment dilemma in the 70s and 80s might have been our rigid labor market. So if people, for example, get fired in Germany, well, they don't have to worry. They get unemployment benefits, social benefits. So they are not really eager to look for a job because they have such high replacement income. Now, once you are unemployed for 2 or 3 years, your human capital depreciates a lot and you cannot find a job that pays as well as your old job. So if your social benefits, your unemployment benefits are pretty high, they might be even higher than the wage you may earn in your new job. And as a consequence, people just stay unemployed, and it's a new steady state that you will approach because of this hysteresis phenomenon. This means that our final steady state or final state in 2100 might depend on the transition and therefore might depend on the shocks during the transition. And if you do not know where you run to, how your final steady state will look like, or the final state, well, then you cannot solve these kind of models by backwards in shooting, and you have a problem. Now, there are some ways out of it. For example, you may use the extended deterministic path. That's also a method that we explain in detail in the book, but they all have some shortcomings. And basically, at least to my knowledge, this problem is not solved in a satisfactory manner in economics and in numerical economics today. And we also doubt that artificial intelligence will solve this problem because all these problems are very idiosyncratic. So you cannot write an algorithm and tell an artificial intelligence unit what to do. So you have to take precautions for many idiosyncratic individual things and to come up with a learning algorithm for artificial intelligence units. That's hard, and many economists like Malia and the couple, Malia and Malia, and many other great economists doubt that over the next 5 to 10 years, the artificial intelligence units will replace you and me, the computational economists. So that's good news. That's why another reason why you should read our book. So to summarize, yes, we provide many methods, also new methods, new material on how to solve transition dynamics and local dynamics using global methods, local perturbation methods, but there are open questions and researchers like me waiting for you, for some young genius like you perhaps, to tackle those problems and tell us how to compute dynamics for stochastic economies. A third novel element that we consider in our third edition, Dynamic General Equilibrium Modeling, with Alfred Mausner, that's the equity premium. Now, you probably know the famous Murray-Prescott equity premium puzzle that bonds pay a smaller interest return than equity. So here in our table 5.5, we summarize these findings. This is a table for data for 15 countries covering the time period from 1870 till 2015, so more than 140 years. And we find that bills, like US Treasury bills, have a mean annual return of 1%, bonds about 2.5%, and equity is 6.9%. So if you look at the difference between equity, stocks returns, and bills, treasury bills, for example, it's around 6% over the last 120 years. And we have a problem to explain this. So as Yoder, Julavik, and Taylor put it, the equity premium puzzle is worse than you think. In the first edition and second edition, we provided one possible explanation. That's the one with incomplete markets and heterogeneous agents. Now in the third edition, we provide a new explanation for this equity premium puzzle, which is a disaster risk model. So the likelihood that there might be a huge disaster like the Great Recession or a war or whatever, this may help to explain the equity premium. And in order to solve this, you need global methods, which we extend in our third edition. Now, the equity premium now poses a certain dilemma for our computational economists, for us computational economists. So let's take a look at a typical problem. This week, today is the 10th of March, when I record this video here on March 5, 2024, you could read this headline in the Financial Times. So Germany to create 200 billion euros to fund to support strained pensions. So what's the idea in our dilemma in Germany, where we basically our pay-as-you-go pension system is close to insolvency in 10 to 15 years? Well, the German government plans to behave like a hedge fund. So they will increase their debt by 200 billion euros over the next 10 years. And they invest the money in the stock market and hope that the return in the stock market is higher than the return they have to pay their debtors, their creditors. The creditors. And with the help of this premium, which we have seen was about 6% over the last 150 years, they will try to pay a part of the pension payments. Well, it's going to be very small parts, so the German annual pension payments are around 500 billions yearly, or go up to 500 billions. And with this kind of idea, they will create something like 5 to 10 billions if they are lucky, and their administrative costs are not so high. So this is just, well, this is very, very little to nothing to solve the problem, but still it helps to appease, of course, the minds in Germany. Well, the problem for us economists now is to compute the implications of this. Why? Well, if the government increases its debt, well, it's very likely that they have to pay higher returns on their government debt. And government debt will also crowd out capital, which also has an effect on the capital return, on equity return in our country, in Germany. And as a consequence, the equity premium is likely to change. So what we need to understand, if we want to see what's the effect of this new German pension policies, and perhaps others will follow, we need to endogenize the equity premium. And this is very, very tricky, especially if you have to use, for example, disaster risk models to justify, to explain the equity premium. Then you have to apply global methods. And there is still a lot of open research questions here, a lot of material the young researcher might think about how to solve these problems and come up with a solution. So if you're looking for a PhD topic or a postdoc material, what you might study, well, this is one of the possible questions: how to endogenize the equity premium in a large scale, let's say overlapping generations model, and wonder how these kind of policies, for example, if Norway builds up huge funds in public funds and invested in the stock markets, or if the German government increases its debt to buy stocks, how this helps to offset the demographic transition and the effects on the pension system, or if it does even make the problem worse. And this is some material that you might find worthwhile studying. And our book, our third edition of Dynamic General Equilibrium Modeling, will give you the necessary tools to tackle these kind of problems. Okay, so let me summarize. What's new in our third edition? We have new chapters and sections on numerical methods, higher order perturbation methods. We introduce simulation-based methods. We have the theory of Gorman preferences aggregation, which makes the computation of heterogeneous agent models very easy, and study the transition in the economic demographic transition in a model. But we also argue that this is a very special case, and usually we are not justified to use Gorman preferences. But as a starting point, it's a good point. But if you want to do more sophisticated, realistic analysis, you have to diverge from Gorman preferences. We study the problem of finding an initial value for large-scale OLG models. So often our model, our steady state, is characterized by 200, 300, sometimes 800, or even more than 1,000 variables. And to come up with an initial guess for the solution for the root-finding algorithm is difficult, and we will show you how. So, we do a lot of multi-dimensional state space applications in large-scale OLG models, but also in the neoclassical growth model, the Ayagari-Boole model. And to tackle these problems, we will also introduce you to the Smolyak's algorithm, so that this is one possible way to reduce the curse of dimensionality that I talked to you in the first problem set here in this talk. We have new applications, the rare disaster theory, which helps us to explain the equity premium. We have new Keynesian model in the spirit of Cristiano and Smith-Wouters, so which is the cornerstone of central bank policies. So the 3,000–4,000 people who work at the Federal Reserve or the European Central Bank, they all knew these kind of models and apply them. And we also have a lot on overlapping generations model with endogenous pensions, so increasing the dimension space of our model. So I hope you find this is worthwhile material to look into our third edition here. We have an extensive web page. You see the address here on this page, but you will find it also below this video, in the description of this video. And of course, you find it in our book on dynamic general equilibrium model. You find this page. So to summarize, thank you for watching this short video on the new material on dynamic general equilibrium modeling, on open questions and research, and I hope you like it. And if you have questions, problems with our book, with the models, with the economic problems that we studied, please feel free to send me an email, and I will be happy to correspond with you.